Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. In the previous module, we had looked at the application of the IFFT and FFT operations in the OFDM at the OFDM transmitter and receiver respectively. We said we can use the IFFT operation to generate the transmit signal in an OFDM system and the FFT operation at the receiver to process the received OFDM signal. Today, let us look at another aspect of OFDM transmission, that is the cyclic prefix. So, today we are going to look at another important aspect in OFDM, which is also termed as the cyclic prefix. So, we are going to look at the cyclic prefix in OFDM or orthogonal frequency division multiplexing systems, all right. So, for this let us start by considering a frequency selective channel. So, what we want to do is we want to start by considering a frequency selective channel. So, let us consider a frequency selective channel, and as we have said before, a frequency selective channel can be modeled as Yn equals the output Yn at time instant n equals H0 xn plus H1 xn minus 1 plus H2 xn minus 2 plus HL minus 1 xn minus L plus 1. This is the model without noise for a frequency selective channel. This is the model for a frequency selective channel. Remember, we had looked at this in the context of CDMA also. We have Yn equals H0 times xn plus H1 times xn minus 1 plus H2 times xn minus 2, so on and so forth until HL minus 1 times xn minus L plus 1. So, this has channel taps H0, H1 unto HL minus 1, that is L channel taps. And we have also seen that the output Yn depends not only on the input symbol xn at time instant n, but it also depends on xn minus 1, xn minus 2, so on until xn minus L plus 1. Therefore, this channel has inter-symbol interference, correct. So, in the time domain, this channel has inter-symbol interference, which is the same thing as frequency selective channel or frequency selective fading in the frequency domain. Therefore, this model of input output symbol, the input output received symbol model with inter-symbol interference represents a frequency selective channel, all right. And now we are going to consider this frequency selective channel in an OFDM system. So, as we said previously, at the OFDM system we generate the transmitted signal or the transmit signal using an IFFT operation. So, let us do the following. Let us consider the first set of symbols x0 tilde, x1 tilde, so on up to xn minus 1 tilde. These are the symbols that are loaded onto the subcarriers, and then I process them using the IFFT operation to generate the samples x tilde 0, x tilde 1, x tilde n minus 1. In the second OFDM symbol, let us say I have samples x0, x1 up to x of n minus 1. I again use the IFFT operation to generate the corresponding samples of the transmit signal x of 0, x of 1, x of n minus 1. So, these are the samples, transmitted samples corresponding to first OFDM symbol the transmit samples of OFDM symbol 1 and these are the transmit samples of OFDM symbol 2. These are the transmit samples of OFDM symbol 2. So, what do we have? What we are saying is, let us consider two consecutive OFDM symbols. So, what we are doing is we are considering the transmission of two consecutive OFDM symbols. The symbols capital X 0, capital X tilde 0, capital X tilde 1, so on until capital X tilde n minus 1 are the symbols of the first OFDM symbol which are loaded onto the various subcarriers. We take the IFFT to generate the transmit samples which are X tilde 0, X tilde 1, small x tilde 0, small x tilde 1, so on until small x tilde n minus 1. Similarly, I have a second OFDM symbol consisting of symbols capital X 0, capital X 1 until capital X n minus 1, of which I am taking the IFFT to generate the transmit samples small x 0, small x 1 up to small x n minus 1, and I am transmitting these over the channel. So, I am considering the transmission of two consecutive OFDM symbols. I am generating the IFFT, using the IFFT I am generating the samples of the first set of symbols, transmitting them, then I am generating the transmit samples using the IFFT for the second OFDM symbols, and I am transmitting these samples again, alright, consecutively. Okay. Now, let us look at the output of this OFDM system. Now, when I look at the output corresponding to x of 0, now here at this point when I look at the output, I have at the output of the frequency selective channel, I have y of 0 equals h of 0 x of 0 plus h of 1 times the previous sample, but the previous sample is x tilde of n minus 1 plus h of 2 times the previous sample, but the previous sample is x tilde of n minus 2. So on and so forth, I have h of L minus 1 times x tilde of n minus L plus 1, and here at this point you can see I have a problem because I have inter-block interference. Now, if you look at this OFDM received OFDM symbol, you can see that y of 0 equals h of 0 times the sample small x 0 plus h of 1 times the previous sample, but the previous sample comes from the previous OFDM symbol, that is x tilde of capital N minus 1 plus h of 2 times x tilde of capital N minus 2, so on and so forth, h of L minus 1 times x tilde of n minus L plus 1. Therefore, what you can see is for the sample small x 0, there is interference from the samples x tilde n minus 1, x tilde n minus 2, so on x tilde n minus L plus 1 from the previous block. Therefore, there is inter-block interference. So, this transmission, so what is happening here, because we have, let me write it again clearly, y of 0 equals h of 0 x of 0 plus h of 1 x tilde of n minus 1 plus h of 2 x tilde n minus 2 plus h of L minus 1 x tilde n minus L plus 1, and what we have over here, if you can see these are the samples from the previous block. So, in this there is what is known as inter block. So, we are seeing a new term here, there is inter block interference or there is IBI. Because of the frequency selective nature of the channel, there is IBI or inter block interference, where the samples in the current block are being interfered by the samples from the previous block in this OFDM or orthogonal frequency division multiplexing system. And now our main motive is to basically avoid this interblock interference or remove this interblock interference in the OFDM system. So, we would like to devise a mechanism to avoid the interblock interference in OFDM, and for that purpose we are going to use the cyclic prefix. So, the cyclic prefix helps avoid the interblock interference in OFDM. What is the cyclic prefix? Now, let us look at the cyclic prefix. I am transmitting, let us consider the symbols x0, x1, x2 up to xn minus 1. These are the symbols that are loaded onto the various subcarriers. I am taking the IFFT to generate the samples x of 0, x of 1, x of 2 until x of n minus 1. Now, instead of directly transmitting these samples, I am going to add a prefix x of n minus 1, x of n minus 2, so on x of n minus L bar. So, what I am taking? I am taking L bar samples and I am prefixing them L prefix of L bar samples from the tail. So, I am taking a prefix of L bar samples from the tail. So, what am I doing over here? If you look carefully, because this is a key step, what am I doing? I have a block of n samples, of n OFDM samples that are generated using the IFFT. In this n samples, I am taking the last L bar samples, that is xn minus 1, xn minus 2, xn minus L bar, these last L bar samples, and I am prefixing them into to the front of this transmitted OFDM samples. So, the total number of samples that I will transmit is n plus L bar, that is the total length of the block has now become n plus L bar. I am adding a prefix of L bar samples from the tail of the OFDM block in the beginning of the OFDM block. So, I am cycling samples from the end of the OFDM block towards the beginning of the OFDM block to add a prefix. Hence, this is known as a cyclic prefix. Let me again clarify this important idea once. I am taking L bar samples from the end or from the tail of the OFDM block. I am cycling them in a cyclic fashion. I am moving them to the prefix of the transmitted OFDM block, and I am adding this prefix to the transmitted OFDM block. Hence, this is known as a cyclic prefix. Alright, so this I am adding a cyclic prefix to the transmitted OFDM samples. And now let us look at the corresponding received OFDM signal. So, now what do I have? I have the OFDM samples with the cyclic prefix. So, I have the samples x0, x1 up to xn minus 1, to which I have added the cyclic prefix x of n minus 1 up to x bar up to x of n minus L bar. This is my prefix, And now if you look at the first symbol, I have y of 0 corresponding to x of 0, I have y of 0 equals h of 0 times x of 0 plus h of 1 times the previous sample, which is x of n minus 1, plus h of 2 times x of n minus 2, plus so on and so forth, h of l minus 1 times x of n minus l plus 1. Because I have prefixed the block with samples from the same block, now what I am seeing is y of 0 is h of 0 times x of 0 plus h of 1 times x of n minus 1 plus so on and so forth, h of l minus 1 times x of n minus l plus 1. So, the interference is now restricted to the samples from the same block, therefore, we have avoided the inter-block interference. By adding the cyclic prefix, we have been able, or we have managed to restrict the inter-symbol interference to samples from the same block. So, in this system with the cyclic prefix, there is inter-symbol interference, but there is no inter-block interference, therefore, we have avoided the inter-block interference, and therefore, thus the cyclic prefix has helped us avoid inter-block interference. Similarly, we have y1 equals h1 times or h0 times x1 plus y1 is the received symbol corresponding to x1, this is h0 times x1 plus h1 times x of 0 plus h2 times x of n minus 1 plus so on h l minus 1 times x of n minus l plus 1. Now, let us look at this pictorially. Let us draw a diagram to represent this, to clarify in greater detail what is happening in this scenario. Now, if you look at this, let me draw the various samples x of 0. I have here x of 1, so on and so forth. I have x of n minus 3, I have x of n minus 2, I have x of n minus 1, and now let me draw a line for time instant 0. At time instant 0, I have h of 0 multiplying x of 0, h of 1 multiplying x of n minus 1, h of 2 multiplying x of n minus 2, h of 3 multiplying n minus 3. So, this is for time instant or this is for n is equal to, this is for n is equal to, at n is equal to 0, what we are saying is we have h 0 multiplying x of 0 plus h 1 times x of n minus 1 plus h 2 times x of n minus 2 plus h 3 times x of n minus 3 and so on. Now, look at n is equal to 1, we have something very interesting, we have h of 0 multiplying x of 1, h of 1 multiplying x of 0 plus h of 2 multiplying x of n minus 1, h of 3 multiplying x of n minus 2, h of 4 multiplying x of n minus 3. So, what you can see is the whole channel, the coefficients of the channel are moving in a circular fashion over the transmitted symbols, right. If you can look at this figure, what you can see is at n equal to 0, I have h of 0 times x of 0 plus h of 1 times x of n minus 1 plus h of 2 times x of n minus 2, so on. At the next transmit instant, that is n equal to 1, the whole coefficients of h have shifted circularly over the transmit symbols. We have h of 0 times x of 1 plus h of 1 times x of 0 plus h of 2 times x of n minus 1 and so on. And if you can look at that, what you can see is that the channel coefficients are moving with each time instant, the channel coefficients are moving circularly over the transmit OFDM samples. Therefore, this output operation is a circular convolution. This operation, that is the output OFDM signal, is a circular convolution. This is a very important idea. Output OFDM signal is circular convolution, is a circular convolution between the channel H and the input X, and this is a very important idea. So, let me repeat that. Adding the cyclic prefix after addition of the cyclic prefix. So, addition of cyclic prefix, which is abbreviated as Cp, has resulted in a circular convolution at the output of adding a cyclic prefix. So, what has happened? We have added a cyclic prefix at the beginning of the transmitted OFDM signal, and as a result what we are observing at the output is, surprisingly, we are observing that the generated samples y0, y1 up to yn minus 1 are obtained from a circular convolution of the channel coefficients h0 of h1 up to hl minus 1 with the transmit samples of the OFDM signals, that is x0, small x0, small x1, small xn minus 1. Therefore, I can now represent it mathematically as, interestingly, I can now represent this mathematically as y equals h circularly convolved with x, where y is the received OFDM samples. This is the channel coefficients or the channel filter, x is the transmitted OFDM samples, and this symbol here, the circle with the star in between, of course denotes the circular convolution. And we know from DSP that if the input, if y is given as a circular convolution between h and x, if I take the FFT or the DFT of this, I will have y of k equals h of k times x of k, because circular convolution in the time domain is equivalent to a product of the DFT coefficients, a product of the FFT coefficients in the frequency domain. That is, if small y is h circularly convolved with x, then if I take the corresponding DFT, then the DFT coefficient yk equals hk times xk, where yk is the DFT coefficient of the signal y, capital Hk is the DFT coefficient of the channel h, and capital Xk is the DFT coefficient of the transmitted signal x. Therefore, what we have now in the DFT domain, we have yk equals hk times xk, and what we have is the kth DFT coefficient of OFDM of the OFDM received signal in fact the received signal is y of 0, y of 1, y of n minus 1. So, I am taking the kth DFT coefficient from the n point DFT or FFT, correct. Now, for HK, HK is the kth DFT or FFT coefficient, of n point FFT of, because H is of length L, I have to 0 pad it. So, H of 0, H of 1, H of L minus 1, and I have obviously n minus L zeros. This is the n point FFT of the 0 padded channel coefficients, and xk is the FFT of xk. Let me write it clearly. This is the FFT of, or the kth FFT coefficient, kth, this is kth DFT coefficient of the samples x of 0, x of 1, x of n minus 1. And this is a very important step in the OFDM. If I look at the FFT, which means I am going back to the frequency domain, therefore, I am looking at the subcarriers. Over the kth subcarrier, very interestingly what I have is yk, that is the kth DFT coefficient of the received OFDM signal equals hk, which is the kth DFT coefficient of the 0 padded channel coefficients h0, h1, hl minus 1 times xk, where xk is the kth DFT coefficient of the OFDM sample small x0, small x1, small xn minus 1. And now also realize that the small x0, small x1, small xn minus 1, these are nothing but these are generated by an IFFT of the OFDM symbols capital X0, capital X1, capital X2, capital X minus 1. So, therefore, when I do the FFT or the DFT, when I do the FFT of this, I get back the symbols x0, xn minus 1, and therefore, it means that x0 equals small x0, x1 equals small x1, xn minus 1 equals small x n minus 1. So, what I am saying is the following thing: the small x's, small x0, small x1, small xn minus 1 are generated by an IFFT of capital X sub 0, capital X sub 1, so on, capital X sub n minus 1. Therefore, once I take the FFT of the small x's, small x0, small x1, small xn minus 1, I basically get back, I basically get capital X0, capital X1, capital X minus 1, which are basically nothing but respectively equal to x, capital X sub 0, capital X sub 1, capital X sub n minus 1. Capital X sub 0, capital X sub 1 until capital X sub n minus 1, initially taking the IFFT to generate the OFDM samples, and then I am generating the FFT again. So, the IFFT and FFT cancel, and I therefore get back the symbols that are loaded onto the kth, onto the each subcarrier. Therefore, very interestingly what I have is yk in an OFDM system after the FFT, yk equals hk times xk. Yk is symbol on kth subcarrier, hk is the coefficient of, or the channel coefficient or the channel coefficient of the kth subcarrier, and xk is the symbol Hk is the symbol that is transmitted on the kth subcarrier, and therefore, now you can see that each subcarrier is experiencing flat fading. Is experiencing and now you can see that each subcarrier is experiencing flat fading, because what do we have? We have y of k equals h of k times x of k. There is no frequency selectivity. The symbol x of k on the subcarrier is multiplied by the channel coefficient x of k to generate the output symbol y of k. Of course, we have ignored the effect of noise, right, but you can see there is no inter-symbol interference. Once we consider each subcarrier, there is no inter-symbol interference, and in fact, this is the motivation with which we set out for OFDM. Remember, orthogonal frequency division multiplexing has an aim to overcome the frequency selective nature of the wireless channel, and now we are seeing with this IFFT FFT operation at the transmitter and receiver respectively, and the addition of the cyclic prefix at the transmitter, what we have been able to do is we have been able to convert this wireless communication system into a frequency flat fading channel across each subcarrier. And how many such subcarriers? Precisely, we have capital N subcarriers. Remember, we said we have capital N subbands. In each of these subbands we have a subcarrier, therefore we have capital N subcarriers. Let me draw this schematically to conclude this module, and therefore if I look at this in a schematic fashion, I have x of 0 which is multiplied by the channel coefficient h of 0 to generate the symbol y of 0 across subcarrier 0. I have x of 1 which is multiplied by the channel coefficient 1 to generate the symbol y of 1, and finally I have also this continues, and finally I have x of n minus 1 multiplied by h of n minus 1 to generate the subcarrier y of n minus 1. So, what I have is basically OFDM has converted frequency selective channel into n flat fading channels. OFDM has converted frequency selective channel into n flat fading. So, what we are seeing is very interestingly the following thing, that is, after I take the FFT at the receiver, it is as if I have n parallel flat fading channels across the n subcarriers, that is, each subcarrier can be thought of as a flat fading channel with input. So, if I look at the kth subcarrier, I have input x of k multiplied by the channel coefficient h of k and the generating the received signal y of k. So, y of k equals capital Y of k equals capital H of k times capital X of k, and therefore, across each such subcarrier k I have a flat fading channel. Total number of subcarriers is n. I have a collection of n parallel flat fading channels. Remember, we said OFDM is a multi-carrier transmission system, whereas in a single carrier transmission system we are transmitting one symbol every time instant 1 over b, where b is the net bandwidth of the system. In an OFDM system, we are transmitting n symbols in parallel over capital N subcarriers, and the time of each OFDM symbol is capital N by b, right. So, we are expanding the time of each symbol, thereby removing the frequency selective nature of the channel or removing intersymbol interference, and now we are seeing basically OFDM converts the frequency selective channel into a set of n parallel flat fading channels, one flat fading channel across each subcarrier. So, these are two very important ideas in OFDM. One is the FFT, IFFT process, IFFT, FFT processing in OFDM, and two is the addition of the cyclic prefix. Alright. So, these are the two key steps in OFDM, and with this let us conclude this module here and let us look at other aspects of OFDM in the subsequent module. Thank you very much.